Okay, the record is now on. The question is whether or not we need to calculate the force on every frame. No, in the old days, computer programs available were only two-dimensional, you know. So engineers could only create one frame at a time. So it would have been something like this, put into the computer program. So it was, yes, important that we calculate the load for every frame. But to answer that question more thoroughly, let's say you don't need to do it every frame. But if supposedly, if I decide to use all the frames here, if I decide to use frame number 1, 2, 3, 4, 5, and 6 to withstand the wind load from the side, I know now that the tributary width for frame number 2, 3, 4, and 5 would be 8 meters, just like this brown color, right? But for frame number 1 and 6, it's going to be half of that. Correct?
Yes, yes.
So I may decide to, you know, perform the analysis on frame number 2, and that would cover frame number 2, 3, 4, and 5. So I have one frame, and let's say if I know that it's not going to affect the size of the structure that much, I may use the same size for frame number 1 and 6. So that means I don't need to calculate the force acting on frame number 1 and 6, assuming that I will use the same frame as number 2. But if you need to calculate, you know, it's not that difficult. It depends on the tributary area. It's not like you are going to have like 200 different tributary widths or something like that. And generally, it's this much. And I have to tell you that, you see, for this building, this side, you know, when you look at the wind coming in this side, you see the frame is pretty long. See, and you have 6 columns in the frame. So in terms of the strength and stiffness, the frame in this direction tend to be stronger, you see?
Yes.
Yeah, because you have more columns. And the frame itself is bigger. So it tends to be stronger. But in this direction, in the purple direction, this is not purple. What color is it? Bracken? I don't know. When the wind comes in this direction, you have shorter frame, and you only have 4 columns. So the frame itself is going to be slightly less stiff, but you have more. So in the end, you may want to use all of them. Okay, and in some cases, you know, I went to look at the lecture last year, and I talked about this building. In some cases, you know, there's a building where, you know, it's very, very thin in one direction. Let's say this is very thin, but long. Because sometimes, you know, the shape of your building will depend on the land requirement. Right? So you could buy a piece of land that looks like this. You're going to have to build a building that looks like this. You see? So let's say when the wind comes in this direction, it's fine, right? Because you have a long frame in this direction, and that means also many columns as well. But when the wind comes in this direction, oh no, you have a very, very narrow frame, and perhaps only 2, 3, 4 columns. So imagining yourself, you know, let's say in the blue direction, you can see yourself standing, you know, with leg widespread like this. So you're going to be very hard to push, right? Because you have a very stable stance. But in the purple direction, you can imagine yourself with the legs tied up. So you stand up like this. So when someone pushes you, you're pretty much ready to go down, right? Because you cannot create more equilibrium for yourself. Because just look at this. If your leg is widespread like this is where your reactions are, right? So you have the moment arm to resist the lateral force. If your reactions are just so tied together like this, so your moment arm becomes so small, so the reactions become humongous. So this is real. You can go back and try to play with your frames when, let's say, you have the same frame. You can make it determinate like this, and then you have some frame like this. The reaction here is going to be a lot larger than this because you don't have the help from the moment arm, right? So let's say this is H, this is P, and this is say, what do I want to call it, B. This force here is going to be P, why do I have to write so small? PH over B, right? So if B is big, you know, your reaction is going to be small. If B is small like this, your reaction is going to be big. And the moment is going to be big as well. So what if you face a situation like this? What are you going to do to ease the pressure of the wind in purple direction? Do you have any suggestion? What do you think?
Like provide a hole that wind
Wow, you're kind of smart. Have you watched
can
the
go
clip
easily.
last year? You have?
No.
No? Yes. Oh, that's one of the very, very good solution. In fact, this happens to a building in Thailand. So there's no way to solve this. So they create a hole here in the building so that the wind will go through here to ease off the pressure, right? And you know, the wind pressure is getting bigger and bigger and bigger the higher you go. So yes, they punch a hole through the building. It's not a small hole, it's a huge hole. It's like a few stories high. And this building is called Taiwan building. Somewhere around Silom, Sathorn, that region. You can see the building. They punch a hole in it to let the wind go through. So when the wind goes through, you know, you don't have a wind load. And sometimes to create a building that looks like this would help as well, you know. Why not? Right? Because the wind is going to flow like that. So when you have some strange shape like this, the good old building code will not help because it doesn't have any reduction or any factor to account for the shape of the building. But the new standard from the, I don't remember, the Department of Urban Planning, the Department of Urban Planning and so and so, they have a very, very good standard to calculate the wind load, which account for a shape like this. And, you know, but when the shape does become extremely crazy, for example, can you recall the condominium by the side of Rama 9 Bridge that has 2 towers like this? They got 2 towers. Not the align as well. You got 2 towers. And then they got the swimming pool, you know, connecting these 2 buildings together like this. But they got swimming pool here. Have you recognized this one? You know, by the Rama 9 Bridge on the expressway. on the Rama the third road, you know, 2 towers with the swimming pool like this. You know, for a case like this, there is no analysis available. You have to build the model and then put it in the wind tunnel to have the wind load analysis in the wind tunnel, because you cannot trust the software to be able to calculate the complicated stuff like this. Okay, so that's it. I think we have covered the general idea of, you know, the lateral load and the tributary area for stuff like this. And I have put the active session in the Facebook group already, and say, I don't think it's too difficult for you. Would you like to have the active session tomorrow, or you think you can handle this by yourself? That's a question. Hey. Hello? Can you handle this by yourself, or would you like to have the active tomorrow? I am okay if you're not going to have one tomorrow because it's just the first week. But this is something that you should be doing in the first week, so that by next week, when we have the active session, you should be doing the slope deflection method, which is a new method. Hello? Anyway, that's a question. I will call for an answer by the end of the class. Okay. So let's say that's it. Then we come back and we don't have anything to do now except to start talking about the method that we are going to use to solve the structure. Okay. This is the first of the displacement method that you're going to learn in class. The first one is what we call the slope deflection. And it's not an overstatement to say that this is the most important method in the world, because after the development of this method, more will flow in the way. The next one you will learn is the moment distribution method. It's also based on this one. It's the mathematical variation of this method. And upon this method, you know, the computer program, so many computer programs have been created. And I can safely say that all the computer programs used in this world right now for structural analysis are based on this method. The general idea is simply developed from something that you are familiar with. It's called F equal to Kx, right? Are you familiar with this one? Or I can say F equals to Kd, where D is the displacement. F is the force, and K is the relationship that can turn the force into the displacement or displacement into the force. This is what we call stiffness. Stiffness is the most important characteristic of the structure. Okay. Now you may recall that in the previous classes, like structural analysis number 1 in the beginning, or in the mechanics of materials, or in the statics, nobody has mentioned much about stiffness, because when you are dealing with the determinate structure, the force is balance itself out in the equilibrium fashion. But when the structure becomes indeterminate, as you can think of in the force method, you remove a redundant to calculate the displacement and use that relationship to solve for the extra unknown force, right? the fact that the force depends on displacement means that the stiffness is important, because you see, force depends on displacement. You solve for displacement, you get the force. You solve for the force, you get the displacement. And the relationship that would turn the force into displacement or vice versa is stiffness. This is the most important thing. Okay. In slope deflection method, you can look at, say, one member. Say what this member is between two joints. Okay. I can draw it like this. Any two joints, I, J. Okay. And it has some kind of arbitrary load, any load acting on it. Any load. So now, one member between two joints with load. When you look at this, they, based on the idea of F equal to KD, it's stiffness, we can separate the joint moments into three categories. Okay, joint moments can be separated into three categories, a long word, so let's just say three groups. Okay, first one, let's say first one, yeah, first is fine, but number one is already there, so let's just say number one with the Roman numeral. It's called fixed end moment. The moment due to the load alone. Okay. The moment due to the load alone. Okay. So that I have to move away all the time. You can say this is a moment due to external load. Okay, that means when I say external load, if you are going to be very, very straight, you know, very direct, it means that no other things involved. This moment is due to the load alone, no displacement, no rotation involved. Okay, meaning we are now looking at this particular member, IJ, without rotation. So I can say that, yeah, it's gonna be fixed, because I'm saying the moment is due to the load alone. So excuse me for a minute or two, okay? All right, so that means I'm saying that the moment is due to the load alone, no rotation involved, no joint translation involved. Okay, so this becomes something like this. And when we're saying that this moment is due to the load alone, the joint is always fixed. Okay, meaning when the joint is fixed and you have the load, we are going to have the internal moment to help resist the load. This is called fixed end moment. And because we are talking about the moment due to the load alone, that means the support conditions of these two joints are always fixed. So when the support conditions are known, the loads are known, it means the fixed end moment can be readily calculated. Okay, for example, if I have the load like this, if it's a uniform load, if I know it's a uniform load, W, I will know that, you know, somebody has done the job for us, but I can do it myself, but it's going to take time. So we're going to have the formulas for this. Say the beam length is L. This moment is going to be equal to WL square over 12. It's a universal number, you should know. And in this slope deflection method, we will use the sign convention, the universal sign convention, that the clockwise rotation is positive. That is the typical sign convention that people use. So when you look at this moment, this is counterclockwise, right? Trying to resist the external load. So this one is negative minus WL squared over 12 always. So this becomes WL squared over 12. So whenever you have the uniform load throughout the span, the fixed end moment is always equal to WL squared over 12. The next one that you should be familiar with is, let's say, the fixed. I will give you the table afterward. Don't worry, but these three that we are the ones that we use the most. Point load in the middle. Okay. The fixed end moment here will be minus PL over 8. And this one is PL over 8. Okay. Another one very useful is this one. And fix, always fix, you see, because we are talking about moment due to load alone, not due to rotation or joint translation. Say P is somewhere. And this is A, this is B, and the length is always L. This one, this moment will become P, A, B square over L square. You know, this is common because you can have point load anywhere on the structure, right? And it is very, very sad that, you know, every year some students manage to mess this formula up. Because you see, after all, it's moment, right? So in the end, the unit of the moment is force multiplied by the length, correct? So you see, if you have the length, the degree of length equal to 3 up top, you have A and then B square. The denominator must be L square, right? In the end, moment comes out to be, you know, force multiplied by the length somewhat. And then somebody will always forget the square down there, up here, and so on and so on. This is your carelessness. And it's not for lack of knowledge, but for lack of, you know, focus, concentration. And it's very sad. And don't forget that this is counterclockwise, so it's negative. And you can guess that for this one, it's going to be P A square B over L square. Okay, so we can have more. We can have the non-uniform distributed load. We can have the, you know, maybe the uniform load that doesn't cover the entire span, something like that. There are formulas for them. No worries. And please, no need to ask. If you have more than one load, superposition applies. Okay. So that's our first category. Moment due to external load alone. Is there any question? This one is pretty straightforward. The second one, I really should try to mix it up a little bit. Okay. The second one is moment due to rotation. Okay, now we have done the part or where we just consider the load and how much the load creates the moment. Now, because your joints will rotate, so that is not enough. We must determine the moment caused by rotation as well. And now this is moment due to rotation alone, nothing to do with the load. Okay, and sometimes I go over this one, not sometimes, every year I go over this one, and it causes slight confusion because this method has been say cut off from the structural analysis class, because I don't think it's necessary for you to understand every method possible, but it's the best way to calculate the moment due to rotation. Anyway, let's say we have now the condition like this. So when the moment due to rotation is going to occur, now we're going to have rotation like this. Say M at Mij, M, the moment at joint I of this member Ij, and then you have Mji. Okay, so it appears that our structure is going to go like this, right? So that's a deformation. So if I am going to draw the bending moment diagram of this beam, the moment diagram is going to look like this. It's complete beam. It's supposed to be parallel. Okay, anyway, so that becomes the moment diagram. Now, the most useful diagram that we can use to calculate the displacement is moment diagram over EI value, right? Or we call it M over EI diagram. So I'm just going to go ahead and, because let's say this is Mij as well, but based on fixed end moment, I should call this Mij, and this is Mji, but this is based on the load. And now this is based on rotation. So I'm just going to put a dash in here to differentiate them. Okay. So the moment diagram becomes Mij prime or dash over EI. That's a value there. And here is minus Mji dash over EI. Now, the most convenient way to calculate the rotation and relate the rotation to the moment, because we are talking about the moment caused by rotation, right, is the use of the method called the conjugate beam. And the method of conjugate beam say that if you put the bending moment diagram here on the beam, remember this is the bending moment diagram of this case. If I put this bending moment diagram on the beam becomes a conjugate beam. That's pretty blunt. But the more important thing is that it says that the rotation of the real beam is equal to the shear of the conjugate beam at that location. Okay. The rotation of the actual beam is equal to the shear of the conjugate beam at that location. So I can now say that my zeta Ij is equal to Vij of the conjugate beam. Okay, so I can now calculate the Vij here by take moment at this location. So I now have the Vij prime multiplied by L. It's going to be equal to the multiplication of this area on top, which is equal to a half of Mij prime over EI multiplied by the length. So that's the entire force here, right? That's one. And then multiply by 2/3, which is the moment arm. 1 second. All right, so let's come back here. You're gonna hear some noise around here because my kids are here having lunch. All right, and so the moment arm here will be 2/3 of an L. Oh, I meant to use the green one so that you can see. Okay, and minus the bottom half, right, which is negative value. So it's a half of Mji prime over EI, again multiplied by L, but this time the moment arm becomes only 1/3. Okay, and this one is the Vij, and we can do the same for similarly, we can say theta Ji is equal to the shear Ji as well, and we can do the same here. And V Ji prime multiplied by L, this time you're going to take moment at this location, right? So it's going to be a half of Mij prime over EI multiplied by L, and then this time the moment arm becomes L over 3 minus a half of Mji prime over EI multiplied by L. This time the moment arm of the negative one becomes 2/3 of L. Okay. 1 second. Okay, so now you got two equations, you solve for them. In the end, you now have the relationship of theta Ij EI over L is equal to Mij over 3 minus Mji over 6, and theta Ji EI over L is equal to Mij over 6 and minus Mji over 3. Okay. Maybe find the better one. And now you can solve for this and put it in the form as Mij prime is equal to 2EI over L, 2 theta Ij plus theta Ji. And then likewise, Mji prime is going to be equal to 2EI over L, 2 theta Ji plus zeta I j. So you can see that the things are taking shape, right? This is the moment, that is displacement, and therefore this little term in front is the stiffness. Okay, and now we only have the relationship of the moment and rotation. That's a second category of the moment. Now there is another one, but the time is running out. Do you want me to finish this? Do you have the class coming afterward? Because we started late by 10 minutes due to the bizarre problem with my computer. Anyway, do you have to do something after this? I can stop the class now and finish the next time. And the third one is moment due to joint displacement. Because your two joints can displace, and when the displacement occur between the two joints, it's going to cause another moment. So that will be the third one. And when we can mix, we can combine these three groups of moment together, and in the end we are going to have what we call the slope deflection equation. Okay, but time is running out, so I can finish this earlier next week. That is fine by me. You can watch the video clip. I believe I have posted the links. Okay, to finish this one. Nobody's responding to me anyway, so I guess I don't mind finishing this up the next time. It's going to take like 5 minutes more, and that's fine. Okay, so let me stop the record. Let's pause it. Okay, so the record is now back on. The last one, now when we look at this, it's the moment due to joint displacement. So we are going to lock the member at the ends, because we are talking about joint displacement alone, not the load, not the rotation. So, okay, now it's going to be Mij double prime this time, Mji double prime. And, you know, our member is going to go like this. No rotation, right? So it has to remain straight. And now you're going to have the moment to resist that. What color did I use? Okay, same thing. So now you can see one thing, that is, because we say we want to use clockwise positive sign convention. So I am rotating the member clockwise. So instead, we are going to have the counterclockwise moment. Okay. And this time again, I am going to use the conjugate beam method. And because of this moment, now the bending moment diagram is going to look like this. Okay. This time, this guy is Mji double prime over EI, and this one becomes minus Mij double prime over EI. Now, this slight complication of the conjugate beam is that because we are now focusing only on the joint displacement, so no rotation, we have to fix both ends. When we use the method of conjugate beam, when you have the fixed support here in the conjugate beam, when you put this load, this bending moment diagram on the beam to create a conjugate beam, you must also alter the support condition into the free. If you have the fixed support, you need to change into the free end in the conjugate beam. That's why I never mentioned it in the class. So crazy enough, we have the member with two free ends. Okay, and then in the conjugate beam, now we know that if we say the rotation of the actual beam is equal to the shear of the conjugate beam, you can guess now the displacement is going to be equal to the moment of the conjugate beam. So okay, so the displacement here, Ji, will be equal to the moment of the conjugate beam. And the moment is simply equal to a half of mji double prime over ei multiplied by L, because we take the moment, so the moment arm is L over 3 for this one, right? Yeah, let's use the green one. L over 3 minus another moment from that piece, a half of mij double prime over ei multiplied by L, but this time this is 2/3 of L. Okay, and in fact, because both moments have to be the same, so this turns out to be say minus ml square over 6 ei. So I can now say that because of the equilibrium, mij is equal to mji, so the moment here equal to mji double prime is equal to minus 6 ei delta over L square. Okay, and that is our delta. So thanks very much for your patience. Now we have every element involved. We have the moment due to the joint displacement alone. We have moment due to joint rotation, and we have the moment due to the load. We combine them and we are going to get what we call the slope deflection equation. And we are going to do that the next time. Okay, thank you very much for your cooperation. And let me stop the video, the record.